Alright, what we want to do in this problem is another statics problem or equilibrium problem, since our object isn't moving, but we're going to take on a slightly more, more interesting problem. And so what we want to do is we want to say that we have two cables suspended from the ceiling, and these cables meet, and they're attached to a third cable that is supporting some mass, M. And so this cable is at some angle theta 1, and this cable is at some angle theta 2. And what we want to do is we want to look at the tensions and understand the tensions in all the different cables involved. So what we'll do is we will break this system down into steps, and we'll attack this system in steps. So the first thing we want to think about is what's going on with the block. So let's break down and just look at the block. So the block has gravity pulling down, the force of gravity pulling down, and it has the force of tension up in the rope against it. And then we'll assume that there's no forces acting on the side to side, and it's just hanging there. So when we look at summing the forces in the Y on the block, we have that it's tension minus the force of gravity, and that has to equal MAY. But because our block is in equilibrium, it's not moving, we know that AY should be equal to 0. So in this case, tension minus FG is equal to 0, or tension equals FG, which is just the M of the block times gravity. So this tension here, that's our tension in this cable, and it has to equal mg. So that's what's in the block. Now we want to move, now that we know this tension, we need to find the tension beneath. So we'll call this tension 1 and that tension 2. So we have a tension in this cable and a tension in that cable. So what does this look like? So when we're going to draw this picture, we have tension here, and we have tension 1 and tension 2. So we're going to need to break our tensions into components. So for tension, let me shrink this up a little bit. So when we're looking at tension 1 has tension 1, here's theta 1, T1. So tension 1y is tension 1 times sine theta 1. And tension 1x is tension 1 times cosine theta 1. But notice that tension 1x points in the negative direction for us. We call that negative direction, that positive direction. So we need to put a negative sign on there. Now we can repeat the same process for the y. We have some force diagram for tension 2, and there's T2x and T2y, and we have our theta here, our theta 2. So the idea is that T2y is T2 times the sine of theta 2, and T2x is T2 cosine theta 2. So when we want to look at what's going on here at this dot, so the idea is that we're now pretending that this dot where the three tensions meet, this dot has to be in equilibrium. Because if tension 1 and tension 2 aren't balancing tension here, then our system would shift around and move. So we're assuming that the system is in equilibrium. So that means when we look at I need to erase this picture of my block. When we look at the sum of the forces in the x and the y, those forces need to sum up and add up to 0, because we don't have an ax, and we don't have an ay at that point. at this point here in our system. So when we look at summing the x's and the y on this diagram, we have the sum of the forces in the x equals max, which equals 0, and the sum of the forces in the y about that point is may is also 0. So let's look at the sum of the forces in the x. Well, the only forces in the x acting on this point are T1x and T2x. So if T2 is positive, we have T2 cosine theta 2 minus T1 cosine theta 1 has to equal 0. So the reason this equation is useful is we can solve this by saying T2 cosine theta 2 equals T1 cosine theta 1. And if we were doing this without numbers, which we are, what this does is this gives us a relation between T2 and T1. So we need this equation. This is a useful equation for us to keep. Now let's look at the sum of the forces in the y. So if we're counting in our system, we count up as positive and down as negative. In this case, what we have is we have T1y plus T2y minus T has to equal 0. So these two y components of the tensions in the cable have to add up to support the tension of the block. Because we know that the tension in this cable from here is the weight of the block. So what we see is we see T1 sine theta 1 plus T2 sine theta 2 has to equal the mg of the block. And if we're gonna go for a solution, what we do is we can now plug in for T2 here, because we can solve for T2, and we can see that T2 is going to be T1. Let's make a little bit more space for that. We'll just temporarily store it up here. So T2 from here, T2 is going to be T1 cosine theta 1 over cosine theta 2. And I know this is a little sticky on the math, but it'll work out. So the idea is we put this T2 into here, and we get T1 sine theta 1 plus T1 cosine theta 1, and then you can see we have sine theta 2 over cosine theta 2, and so that becomes tan theta 2 has to equal mg. Now, if we were looking to get T1, we can factor out a T1, and then you have this ugly thing of sine theta 1 plus cosine theta 1 times tan of theta 2 equals mg. And then you could move this and divide mg. I know that's not real pretty, but you could move this and divide by mg to get T1. Once you have your T1, you can plug it back into here, you get T2, and you now know your tension here, you know your tension here, and you know your tension here. So to review what you would want to do when you have some type of situation where you have multiple forces acting, you first want to look at, you have to break it into two different pieces. The first one being, what are the forces acting on my block, which gave us this tension because we looked at the forces in the y on the block, and that was tension minus Fg was equal to 0 because the block is in equilibrium, so the tension was equal to mg. Then we go and look at this node here where the three cables meet. So in this case, the forces acting on that node are T1, T2, and T. So in order to understand what was going on, we had to take T1 and T2 and break them into their x and y components. So we had a T1y, a T1x, a T2y, and a T2x. So what we realized, though, is that T1 was pointing in our negative direction, so T1x had to be negative. So the next part is we came in and summed our forces in the x and our forces in the y. And the x equation was good because it gave us an extra way to relate T2 to T1 through the fact that they have to be equal and opposite to stay balanced in the x direction, since we have no motion in the x. And that gave us our relation between T2 and T1. Then we solved the sum of the forces in the y, and we said that it's not moving up or down in the y. And the three forces in the y were T1y and T2y. Those two have to add up to be the tension pulling down. And that had to be 0 because it's in equilibrium. So we then came in and plugged in. We got this ugly thing with the T1 by substituting in for T2. And we had the T1 like this, in this term of sine theta 1 plus cosine theta 1 times tan theta 2 was equal to mg. And that enabled us to solve for T1. Once you have a number here for T1, you plug back in here to get T2. And that's how we would solve this problem.